Welcome friends, Igor is here, and in this video we will talk about the subject of linear algebra. This is an introduction to a one-semester course in linear algebra. In this video I will give you some motivation and a little bit of flavor of linear algebra. Linear algebra is a key core course in the mathematics curriculum. It allows students to see the full development of a coherent body of knowledge from ground zero. Moreover, this body of knowledge has profound applications in many areas of life. These applications skyrocketed recently with the widespread use of search optimization algorithms and machine learning. In this course, we will cover the following topics: systems of linear equations and how to solve them, column vectors, matrix operations and their properties, abstract vector spaces, determinants of matrices, eigenvalues and eigenvectors, linear transformations between vector spaces, and finally, representations of vector spaces and linear transformations. Linear algebra is one of few mathematical subjects that achieves the ultimate goal of complete classification of the objects it studies. By the end of this course, we will be able to classify all finite dimensional vector spaces, and this classification will turn out to be super simple. The term linear algebra consists of two words, linear and algebra, and I will start by briefly looking into the meaning of these terms. Linear is a term that we will fully understand and appreciate only towards the end of this course, and in fact, understanding what this term really means is one of the goals of this course. But for now, intuitionally, think of linear as something that is simple, straight, or flat. For example, a straight line in a two-dimensional plane is that straight, simple, linear object. And something that is curvy, is complicated, it's nonlinear. Well, if there is one lesson you are to get from this slide, it's this: do not drink a bottle of vodka before drawing the pictures. So we have this intuitional understanding of the term linear in geometric terms, meaning something straight or flat. But these geometric notions can also be described using algebraic equations. And these equations have, again, that simple, what we call linear form. For example, a straight line in a two-dimensional plane can be described by a simple linear equation in two variables. Also, a two-dimensional flat plane in three-dimensional space can be described by one single linear equation in three variables. The term algebra originates from Arabic, and it is believed to have been introduced in the 9th century as a means to solve some simple equation. That kind of means the reunion of the broken parts, or the way to rearrange terms in an equation to be able to solve this equation. So this historic perspective tells us that algebra was born as a science of solving equations, and as such, it reached its peak in the 16th century with the discovery of general formulas for the cubic and quartic equations. We can express roots of these equations using simple arithmetic operations in terms of the coefficients of the equation. Yet all efforts to solve the quintic equation produced no results for several centuries, until a real breakthrough happened when in 1824 Niels Abel proved the insolvability of the quintic. Just imagine the power of this result. It was proved that the formula for the roots of the quintic equations simply does not exist. And that meant essentially the death of the algebra as science of solving equations. The algebra is dead, long live the algebra. What it meant is the new age algebra had to adapt to this situation, and it transformed into the science of studying algebraic structures. Algebra as science has progressed from answering simple concrete questions such as solving specific equations to studying general abstract algebraic structures. We are going to observe a similar development in this linear algebra course. We will start with simple concrete questions such as solving systems of linear equations, and we will gradually progress to dealing with abstract algebraic structures such as vector spaces and linear transformations between vector spaces. I wanted to give you a motivating example for our first steps towards mastering linear algebra. This example is adopted from an open source textbook, A First Course in Linear Algebra by Robert Beezer. I recommend this book as a companion text to this video course. A link to this excellent free resource is provided in the video description. Imagine that you're the production manager at a food packaging plant, and one of the lines that you're responsible for is trail mix. It's a snack which contains raisins, peanuts, and chocolate pieces. By varying the combination of ingredients, the company produces 3 varieties of this mix: a fancy version, a standard version, and the bulk version. They differ in the allocation of ingredients and, of course, in the final price. The plant has limited storage capacity, and each morning you receive a fixed shipment of 3 types of ingredients. Your main duty as a production manager is to decide how much of each mix to make every day. And of course, you would like to maximize the efficiency of the production, so your main goal is to exhaust all raw ingredients every day. The plant workers mix the ingredients in 15-kilogram batches. And the following table gives you the entire information about this process. Please take a minute to study this table. Each row of the table corresponds to the distribution of ingredients among different types of mix. For example, the 15 kilograms of the bulk mix consists of 7 kilograms of raisins, 6 kilograms of peanuts, and 2 kilograms of chocolate. Now, each ingredient has a cost. Raisins are the least expensive. Chocolate is the most expensive ingredient. Also, based on the proportion of ingredients in each mix, we can compute the cost of ingredients in each corresponding mix. And the table also gives the sale price of each mix at a retail store. Your job is to decide on the amount of each mix to make. And let's keep the ultimate goal in mind. Your goal is to use up all the given ingredients every single day. So let's try to construct a mathematical model and solve this model. We don't know how much of each mix to produce, and therefore let's use variables to denote the unknown quantities. We are going to denote by B the unknown amount of bulk mix, by S the amount of standard mix, and by F the amount of fancy mix to produce. So our goal is to find the values of B, S, and F. Let's keep the practical original problem in mind. In particular, it means right away that our quantities cannot be negative. Also, our main driving factor to deciding how much of each mix to produce is to use up all the ingredients. So let's use the table to construct equations that tell us that we use up all the ingredients. First of all, we would like to use up all the raisins. So let's look at the column which corresponds to raisins. Now, 7 of the 15th amount of bulk mix is raisins, 6 of 15th of standard mix is raisins, and 2 of the 15th of the fancy mix is raisins. All of this should add up to 380 kilograms. So this allows us to construct a first equation that says we are going to use up all the raisins. So part of the raisins goes into the bulk mix, part of the raisins goes into the standard mix, and part of the raisins goes into the fancy mix. Next, let's do the same for peanuts. We would like to use up all the peanuts, and we see that peanuts comprise 6/15 of the bulk mix, 4/15 of the standard mix, and 5/15 of the fancy mix. And this should add up to the total of 500 kilograms. And this gives us a second equation which says we would like to use up all the peanuts. Finally, let's look at the chocolate column. Chocolate comprises 2/15 of the bulk mix, 5/15 of the standard mix, and 8/15 of the fancy mix. All in all, this should add up to 620, and so we get the equation for the chocolate chips. What we have now is a system of three equations, and notice that three equations look very similar. We are going to call these linear equations. So we have a system of three linear equations, and it just so happened that this system has exactly one solution. This solution is given by b equals 300, s equals 300, and f equals 900. Now, it is not yet clear how I got this solution, but at least you can check that this is indeed a solution to this linear system, because if you substitute these values for b, s, and f, they will satisfy every single equation in the system. This gives an initial motivation for our study of linear algebra. We would like to be able to solve such linear systems and show that, for example, in this case, that solution is indeed unique. Now, we did a great job with our main duties, but as a production manager, we have to report to the CEO of the company. And of course, the CEO is not interested in hearing your excitement about how you learned to solve linear systems, how you constructed the mathematical model, and how you solved it. The CEO cares about the profits. Show me the money. And so when we prepare for this meeting, let's try to estimate the possible profit from our production schedule. Let's go back to the table again, and for simplicity, we're going to assume that the profit is the difference between the sale price and the cost of production of each type of mix. So we take the difference in the price and we multiply this difference by the amount of each mix we produce, and that gives us a computation of $2,727 for the total daily profit from this production schedule. Now you're happy that you solved this problem and you're riding this wave, but things do not stay the same. And marketing department decided to standardize the distribution of peanuts among three types of mixes. The revised recipes will include equal amounts of peanuts in all three types of mixes, and this change will be implemented by also adjusting the amount of chocolate pieces. Now, this, in effect, has changed slightly the cost of each type of mix, and the new system of linear equations looks as follows. So I'm not going to go again through the step-by-step construction of each of the equations. We've done this before. This is an updated system based on the new distribution of ingredients. But this seemingly small change has a drastic effect. This new system of linear equations has infinitely many solutions. Let me convince you that the new system has infinitely many solutions. Now, this may look like a trick, like I pulled a rabbit out of a hat, but hold on for now. So let's do the following. I'm going to keep the amount of fancy mix as an unknown quantity f. But then based on f, I will tell you how much of the bulk mix and standard mix to produce. Now, it is easy to check that this is indeed a solution to our linear system regardless of what value of f you use. Because if we substitute these values into each of these equations will simplify to the same fixed values no matter what f is. Of course, you may wonder how I knew to use these amounts for substitutions, but soon we will see that there is no magic in this, and we will have an algorithmic procedure for describing such solutions. But let's not lose our focus, and let's recall that the underlying problem is a practical problem that has some natural limitations. For example, we cannot make negative amounts of each mix. Also, it would be natural to assume that the amounts of each mix is given as integer kilograms, because, for example, how can you create a square root of 2 kilograms? You can't possibly practically measure this amount. But even looking at the requirement that the amounts of each mix be non-negative gives us the following considerations. The amount of bulk mix must be non-negative, and that means f, the amount of fancy mix, must be at least 825 kilograms. Also, the amount of standard mix must be non-negative, and that puts a restriction on f to be no more than 960. putting this together gives us, in fact, a finite set of practical choices. We have to choose one of these 136 values, each of which is going to ensure that we exhaust a daily supply of raw ingredients. So you have this set of equal choices, and which one would you choose? How would you base your decision? Well, let's recall that we have a meeting with the CEO who cares about the profits. So let's add a profit consideration to our decision process. So with this production schedule, we can compute the value of the profit, and we see that the coefficient on F is negative, and that means that producing fancy mix is detrimental to our profits. Therefore, the optimal choice is to produce as little of fancy mix as possible. That means we will produce 825 kilograms of the fancy mix. And now, once the value of F is fixed, we can compute the values of the other types of mixes. B turns out to be 0, and that means we have to stop producing the bulk mix entirely, and S becomes 675 kilograms. Now you're ecstatic because you used both mathematical modeling and common sense considerations to come up with the optimal plan. But you should have learned by now that things never stay the same. And the sales department now tells us that due to increased competition, we have to change the price of the standard mix that we charge. This change in price has no effect on our production schedule because our production schedule is dictated mainly by our goal to exhaust all the ingredients. But what it does change is the profit computation. And now with this new setting, the coefficient on F becomes positive, and that means it is beneficial for our profit to produce as much fancy mix as possible, and therefore the optimal choice is to produce 960 kilograms of the fancy mix. And that means that S becomes 0, and therefore the increased competition and lower price drove us out of the business of producing the standard mix, but we now produce 540 kilograms of the bulk mix. If you found this video helpful, please like and subscribe to help others discover this content. In the next video in this series, we will talk about systems of linear equations and the strategy for solving these systems. I will see you later.